All right, so now we come to the second definition here, and this is just going to capture what we saw with our motivating example, namely we want to look at those algebraic structures, so those rings that don't have zero divisors. These things that, while are interesting, we're going to avoid when we try to look at factorization. So what is our definition? Well, a commutative ring R without zero divisors, or let me put it this way, that has no zero divisors, is called an integral domain. Integral because it sort of mimics what happens in the integers, or just domain. They'll be used interchangeably. Okay, so in particular, the way in which we're going to capture those structures without zero divisors is we're also going to impose a commutativity restraint. Okay, so commutative ring R without zero divisors will be called an integral domain. So as some examples, well, if this is modeled on the integer, Z had better be a domain, and it is, and we saw that earlier, that Z has no zero divisors. In fact, Z adjoin X is also a domain. We saw that earlier as well. In fact, F adjoin X is a domain as well, whenever F is a field. And I'll formalize that result here in a second. Let's look at some other maybe less clear Z mod 8 is not a domain because 2, 4, and 6 are zero divisors. And domains have no zero divisors, so it's not a domain. Let's see, Z19 is a domain because 19 is prime. And we saw that whenever our modulus was prime, we have no zero divisors. And things like R and C and Q, these are all domains too. So any field itself is a domain. We don't have to join X. It's just automatically a domain.